Okay, so today we're going to continue with our unit on covalent bonding and look at what's called the molecular orbital model. So we talked about the localized electron model, but there are some issues with it. First, it assumes that electrons are localized, which means they're located on that particular atom, but we know that we need to add in resonance. And so with resonance, we can have more than one Lewis structure, and we kind of think about the electrons as moving from atom to atom within the bonds. So we need to account for that. Also, the localized electron model doesn't deal with unpaired electrons, and sometimes unpaired electrons are going to come up. And it also gives no information about bond energy, so we need a new model. And so we have what's called the molecular orbital model, and it's the model used to describe bonding. And so we have what are called molecular orbits, or MOs. And they have similar characteristics as atomic orbitals. They hold two electrons with opposite spins, and the square of the molecular orbital wave function indicates the electron probability. Okay, so let's look at a hydrogen molecule. So to obtain the hydrogen molecule's orbitals, we assume they are constructed from 1s because that's where the valence electrons are coming from. We can have two molecular orbitals. MO sub 1 is 1s sub a plus 1s sub b, and molecular orbital 2 is 1s sub a minus 1s sub b. So 1s sub a and 1s sub b represent the 1s orbitals from the two separated H atoms, and these are what make up that H2 molecule. Orbital properties that are of most interest are the size, the shape, which would be based on electron probability distribution, and the amount of energy. And we'll get into energy in a minute. Okay, so if we look at the molecular orbital model for hydrogen, okay, these represent each hydrogen atom that is donating its electron. And then we have what's called a bonding molecular orbital and an anti-bonding molecular orbital, and we will talk about the difference between those in a second. Okay, but we are filling our bonding molecular orbital with opposite electron spins. Okay, and then we've also got shape coming into play here. Okay, and as we move from bonding, to anti-bonding orbitals, we're increasing the amount of energy, and we'll talk about how that relates to the compound. Okay, so let's talk about some important points. Electron probability for both molecular orbitals is centered along the line passing through the two nuclei of the two hydrogens in the bond. For MO sub 1, it's between the nuclei, and for MO sub 2, it's on either side of the nuclei, and these are described as sigma molecular orbitals. So if you remember from the picture, that's why we have the sigma sign here and here. Only the molecular orbitals are available for occupation by electrons. So we're going to say that 1s atomic orbitals don't exist for this. H2 molecule has its own set of orbitals, and we're calling them molecular orbitals. But they are very similar. Okay, so MO sub 1 is lower in energy than the 1s orbitals of the free hydrogen atoms, and MO sub 2 is higher in energy than the 1s orbitals. And MO sub 1 is what's known as that bonding molecular orbital, and MO sub 2 is what's known as the anti-bonding. So if you remember from the picture, that top one had the little asterisk. That's MO sub 2. That's called anti-bonding, and we'll talk about that in a minute. Actually, right now. Okay, so molecules or atoms will always favor the situation with the lowest amount of energy. Well, that would be MO sub 1 then, because it's lower in energy than the orbitals of the free atoms, and so they're going to want to go there. This is called pro-bonding or bonding, and it's lower in energy. And then we have our anti-bonding, which is our MO sub 2 or our sigma with the little asterisk symbol, and it has more energy than the free hydrogen atom. So they're going to want to go to the pro-bonding. If they're forced into anti-bonding, the electrons will occupy that pro-bonding because they want to be stable. So a bonding molecular orbital is lower in energy, and an anti-bonding molecular orbital is higher in energy, and that's where we get the little asterisk symbol. So the molecular orbital model produces electron distributions and energies that agree with our basic ideas of bonding, and so we would say that the model is physically reasonable. It does make sense. So for MO sub 1, the electron probability is between the nuclei, and the electrons can lower their energy by going to that orbital, and that's what they're going to do. For MO sub 2, or the anti-bonding, the electron probability is outside the space between the nuclei, and it's not going to provide any bonding force, and it's going to make it higher energy, so they're not going to want to go there. Okay, labels on the molecular orbits indicate their shape, the parent atomic orbitals, and whether they are bonding or antibonding. So we talked about how antibonding is indicated with an asterisk, and for the hydrogen molecule, both molecular orbitals have sigma symmetry, and both are constructed from the hydrogen 1s atomic orbitals. So that's why instead of saying MO sub 1, we're going to call it sigma sub 1s. So here we're indicating the parent atomic orbital, and then also the shape. And then MO sub 2, our antibonding, is sigma 1s with an asterisk. So we can also write molecular electron configuration from this model, and it's similar to atomic electron configuration. So the H2 molecule has 2 electrons. They're both in the sigma 1s molecular orbital, and so we would say that the electron configuration is sigma 1s and then the 2, indicating kind of like, you know, how we say 1s2. Well, now we've got the molecular orbital, so it's sigma 1s2. Each molecular orbital can hold 2 electrons, just like the atomic orbitals, and the spins have to be opposites. And orbitals are conserved, so the number of molecular orbitals is always going to be the same as the number of atomic orbitals that was used to construct them. Okay, let's look at another example. So the H2 1- ion. This is formed from the H- ion and the hydrogen atom. So we have the H- ion's electron configuration is 1s2, and the hydrogen atom is 1s1. We're going to use the 1s atomic orbital for the molecular orbital diagram, because that's where all of our valence electrons are coming from. And the electron configuration would then be sigma 1s2 and sigma 1s asterisk 1. Okay, let's look at a picture of this before we go on. So let's see. We've got our H- ion and our H atom. And so this is contributing 2 electrons, and this is contributing 1 electron. And then we have our antibonding. Okay, I'm a little not quite split evenly. And our bonding. And so then we're going to first fill the lower energy, which is our sigma 1s, and then we're going to fill our higher energy, which is our sigma 1s asterisk or antibonding, and we've got 1 left, so we'll point it up. And so our electron configuration becomes sigma 1s2, so that's because we have 2 here, and then sigma 1s asterisk 1 because we have 1 electron in that molecular orbital. So the H2- ion will be stable if it has lower energy than its separated parts, right? Things are going to form compounds if it makes them lower in energy. So in the molecule, 2 electrons are in the bonding orbital, okay, and that's these, and then 1 is in the antibonding. And since more electrons are favoring the bonding versus antibonding, this is lower in energy, and so we would say that the molecule is favored. So H2- ion will exist, and it will be a favored structure. Okay, so let's talk a little bit about bond order. This is the difference between the number of bonding electrons and the number of antibonding electrons divided by 2. And we divide by 2 because electrons occur in pairs. Okay, so for the H2 neutral molecule, okay, if you remember, we had, it looked a little bit like this. We had 1 donated from each, and then both went into the bonding orbital, none into the antibonding. And so we had 2 minus 0 over 2, and that gave us a bond order of 1. So for the H2- ion, okay, that one looked like, okay, we had 2 from the H-, 1 from the H, 2 filled the bonding, 1 filled the antibonding. So we had 2 minus 1, so 1 over 2, that gave us 0.5. And so we've got, okay, here, let's see. Okay, so we've got a smaller bond order for the H2- ion than we do for the H2 neutral molecule. So bond order is an implication of bond strength because it reflects the difference between the number of bonded electrons and antibonded electrons. So a larger bond order means a greater strength. And so for our example, this would be H2 because it had a bond order of 1, whereas the H2- ion had a bond order of 0.5. So let's take a look at helium. So for He, the helium molecule, there are 4 electrons. 2 get raised in energy or in antibonding, and 2 are lowered in energy or in the bonding or molecular orbital. And so if we look at that one, 2 minus 2 over 2 is 0. Well, that's a really low bond order, so it's probably not going to be favored. So what this means is that helium would prefer to be alone than to be bonded in a molecule, which makes sense because helium is a noble gas. Okay, so here is helium's molecular orbital. Helium on its own, each one is donating 2 electrons. We fill our lower energy molecular orbital, and then we have 2 left. So we fill our higher energy antibonding molecular orbital, and so then we would get 2 minus 2 over 2. So we would get 0. Okay, so let's predict the bond order for the following. Okay, so let's do H2 2 minus first. Okay, so H2 2 minus contributes 4 electrons. So let's draw our orbital. Okay, so we've got our H1s and our H1s, and so if we've got 4 electrons, let's see, so we have 2 in the lower energy sigma 1s, and we have 2 in the higher energy antibonding 1s. And so then if we look at bond order, this is equal to bonding electrons minus antibonding electrons over 2. So we have 2 of those minus 2 of those over 2, and that's going to give us 0, which means that this molecule is not favored. So then if we look at H2 plus, okay, well here we've got 1 electron, because each hydrogen donates 1, but then the plus means it lost 1, so that's 1 electron. Okay, so then we've got our H1s and our H from the 1s, and we only have 1 electron, so that has to fill our lower energy orbital, and this is our higher energy, but we don't have any electrons left. So if we look at bond order here, this is 1 bonded electron minus no antibonded electrons over 2, and that gives us a bond order of 0.5. So this molecule is favored, but not very much. Okay, so we're still going to have separate hydrogen atoms, but H2 plus could be seen. Okay, so before we get to the check for understanding questions for section 2 on the molecular orbital model, here's the chemistry cat joke. So maybe we're all feeling this way about the chemistry cat jokes, but don't worry, there are plenty more where that came from. So let's look at section 2. Okay, so number 1, summarize the problems associated with the localized electron model. Number 2, what is the difference between the pro-bonding orbital and the anti-bonding orbital, and which is favored and why? Number 3, what is the difference between writing the regular electron configuration that we've done before and writing the electron configuration using the molecular orbital model? Number 4, how can you use the molecular orbital model to predict if a molecule is favored? And number 5, what is bond order? And what is the relationship between bond order and bond strength? Okay, so give these a try and we'll discuss them in class. Have a good day.